In section 4.1, we look at inverse functions. In particular, we identify one-to-one functions, determine whether two functions are inverses of each other, and then find the inverse function and its domain. So to start with inverse functions, we first must understand the concept of a one-to-one function. So a one-to-one function, f is one-to-one, and I'll go ahead and show you the abbreviation for one-to-one. It's 1-1, one-to-one. If, when f of A is equal to f of B, then the A must be equal to B. Now, that's a lot of algebraic symbols. Let's break it down. First, start with the assumption that f of A, so the function evaluated at x equals A, is equal to the same value as when f is evaluated at x equals B. Okay. A function is one-to-one if, when you try to make this statement, then you have no leeway in what the A is equal to. It has to be equal to the other element. In other words, evaluating f at A, there is no other value of x that produces the same value as f of A, and so the A and the B are all equal. It's sort of math jargon for saying nothing else can possibly happen. The A and the B, they're the same. It was all fake to begin with. Okay? Now, in sort of layman terms, what this says is that each y value is associated with only one x value. Now, we may have talked about something like this before when we talked about functions, but with functions, it was the other way around. A function is there is only one x value associated with each y value. So this is the sort of the switch of that. And that's going to be a recurring theme as we go on today. So this is opposite of function definition. That is the opposite of the function definition. So you determine if a function is one-to-one, if for each y value there is only one x value. If there are multiple x values, then it's not going to be one-to-one. Let's take a look at example 1. So f is equal to the function, or maybe relation, I don't know yet, of this set of ordered pairs. 3, 2, 5, 8, negative 1, 8. Determine if this f is one-to-one. So you look at the y values. Do you have repeating y values? Yes. The 8s repeat. Then you check the x values. Were they the same x value? In other words, was there only one x value that was related to the y value of 8? The answer is no. So repeated y's, but different x's. That is not one-to-one. Okay. So the definition of one-to-one is for some y value, then if you have that y value repeated, then the x values must be repeated. These x values are different, so it's not one-to-one. Let's look at example 2. G is equal to negative 5, 3, 9, 2, and 0, 15. Is G one-to-one? So first you check to see if any of the y values repeat. They do not. So no repeated y values. So we're good to go. That's one-to-one. Now there's a graphical way of determining if a function is one-to-one. It is called the horizontal line test. It's horizontal line test as opposed to vertical line test because we're not thinking about the x's this time as we were with the vertical line test. We are thinking about the y's. And so it has to be a horizontal line test. The horizontal line test says the following. oops, a function is 1-to-1 if no horizontal line intersects the graph in more than one point. All right, so if a horizontal line does intersect the graph in more than one point, then that means there is one y value with two different x values. So the quintessential example of a function that is not 1-to-1 is the parabola. Take your typical parabola, take a horizontal line, and you see that we have these 2 points. Now since we're on a horizontal line, they have the same y value, but it intersects the graph here on the left. I'll say that that's x1, and here at x2. Those are obviously different x's, so this would be not 1-to-1. Let's look at some examples on page 2. Determine if the relations graphed below are 1-to-1 or not. So the first one, you want to apply the horizontal line test. Can you find a horizontal line that passes through more than one point through this graph? And the answer is yes, you bet. Let's just draw one right here. You can draw it several places, but this one intersects it once, twice, 3 times. That is not 1-to-1. The next example, apply the horizontal line test. Can you sweep through from down to up and only hit the graph one time with each of your horizontal lines? Yes, this is 1-to-1. So you can sweep through that graph. There is no place where it's going to intersect the graph more than once. How about this third example? This is some sort of sine curve. Is this 1-to-1 or not 1-to-1? Not 1-to-1. How many times does this horizontal line intersect this graph? Infinitely many. Infinitely many. Here's like 10 of them, maybe. I don't even know. I'm not even going to count. But then this just keeps going. It just keeps wiggling throughout infinities. So it's going to hit it infinitely many times. That is not 1-to-1. How about the graph on the right? Is the graph on the right 1-to-1 or not 1-to-1? Sweep a horizontal line through it. It never intersects more than once. It is 1-to-1. Is this graph on the right a function? No, that's the vertical line test. The vertical line hits it more than once, but the horizontal lines do not. So this is an example of a relation that is 1-to-1, but not a function. All right, let's look at example 4. Show algebraically that f of x is equal to 3x minus 4 is 1-to-1. So to do this algebraically, what that means to do is to start with f of a is equal to f of b, and then show that a is equal to b. So you're going to start with f of a is equal to f of b. You're going to work it, you're going to do something, and then you will end up with a is equal to b. So let's start right here. F of a is equal to f of b. F of a means to plug a into the function. The function is 3x minus 4. So that's going to be 3a minus 4. F of b means to plug b into the function. That's going to be 3b minus 4. And now, really what you want to try to do is solve for A, and then see if you get B. I'm going to add 4 to both sides. So that's going to give me 3A is equal to 3B. From there, I'm going to divide both sides by 3. And I get A is equal to B. Check. So that is a one-to-one function. So if you get A is equal to B, you have a one-to-one function. Again, the question is, when you start solving for A, does that force the value of A to be exactly equal to B? Must that be the case? And that is the question you were trying to answer. Let's look at example 5 on the next page. Show algebraically that g of x is equal to x squared is not a one-to-one function. So at this time we'll start with g of A is equal to g of B. If we are going to show that a function is not one-to-one, then that means there is some leeway with what the value of A could be equal to. G of A, the function is x squared, so g of A is A squared. G of B is B squared. Take the square root of both sides, and I'll use A on one side, but what kind of leeway do I have with the square root of B, square root of B squared? It is plus or minus B. And that separates into two pieces. A is either equal to B or A is equal to negative B. That is the problem. So this means it is not one-to-one. In other words, knowing what A was did not force the B to be equal to the A. It could have been the opposite of A. Right? As a concrete example to this, suppose we're still using the squaring function, and I say that 9 is equal to 9. But in the process of getting 9, what two numbers could I have squared to get 9? Positive 3 and negative 3. And these two things are not the same. A function is one-to-one when you can perform the function and those two results had to come from the exact same number. Since getting a 9 with the square function could come from either negative 3 or positive 3, the square function is not one-to-one. So again, one-to-one means for each y value there was only one x value. All right, let's take a look at inverse functions. Let f be a one-to-one function. So to start to find an inverse, you got to have a one-to-one function. Then g is the inverse of f if these two things happen. You take f composed with g of x, and that is equal to x for all x in the domain of the g function, the rightmost function, and g composed with f of x is equal to x for all x in the domain of f. So an inverse function is a function that undoes a previous function. If you take a function f and the inverse of that function is g, then by taking a number and applying f, you will get some other number. And then by applying g, you should get back to the original number that you started with. You already know lots of inverse functions. Here's one. Add 3, subtract 3. That's an example of two inverse functions, right? Because you start with a number. Let's say you start with 10. You add 3, and you get 13. What function then undoes adding 3? Subtracting 3. 13 minus 3 is back to 10, the original number. And so it works for any number that you could do that to. Multiplying and dividing, those are inverses. Squaring and square rooting is almost inverses. We'll get to that. Cubing and cube rooting is definitely an inverse, right? But we already saw problems with the square function, so we'll have to address that as it comes up. The notation here, g is equal to f inverse. So that's a little -1 as an exponent. Now, don't get confused. The -1 is not an exponent. It's in the same position as an exponent, but it is not an exponent. That is the strictly just inverse notation. Example 6. Show that f of x is equal to 3x minus 4 and g of x equal to x plus 4 over 3 are inverses of each other. So to show that we have inverses, we're going to run these two rules. We'll take the compositions both ways, and then we just need to ensure that we end up with exactly x on the other side. So the first one is f composed with g of x. This would be f of g of x. I'll take the g of x, which is x plus 4 over 3, and put that into the f function. The f function is 3x minus 4, so it's going to be 3 times x plus 4 over 3 minus 4. In the first step, we see that the 3's cancel. That leaves me with x plus 4 minus 4. And then you see that the 4's cancel. And that leaves me with exactly x. So the first half is complete. Now it also has to work for the back half as well. So now we will do g composed with f of x. This would be g of f of x f of x is 3x minus 4, so we apply that into the g function. The g function is x plus 4 over 3, so we're going to plug in 3x minus 4 in the x position, add 4, and divide by 3. You can see that the 4's cancel, leaving me with 3x over 3. And then if you have 3x over 3, the 3's cancel, and that leaves me with x. Check. So since we were able to do the composition both ways, we have an inverse function. And we can say that g is equal to f inverse, or you can say that f is equal to g inverse. Those are the same things. And that is how you show that two functions are inverses of each other. On page 4, we have how to find the inverse function. So this is some general rules. Number 1, replace the f of x by y. Interchange x and y, which literally means where there was an x, write a y. Where there was a y, write an x. You interchange them. Step 3, solve for y, and then replace that in step 4 by f inverse. Example 7. Find the inverse function for f of x is equal to 2x minus 3. Graph both f and f inverse on the same graph. So first, I'm going to rewrite the original function as y is equal to 2x minus 3. Step 2, interchange the x and the y. So where there was a y, we wrote an x. Where there was an x, we wrote a y. Next, solve for this y. So I'm going to move the 3 to the left side. That gives me x plus 3 is equal to 2y. And now, divide by 2. So we get x plus 3 divided by 2 is equal to y. And we want to write that as an inverse function. So f inverse of x is equal to x plus 3 over 2. Let's go ahead and graph these two functions on the same grid. So we're going to have a y-intercept of -3 and then a slope of 2, so up 2 over 1, up 2 over 1. Now I'm going to graph the inverse function. The easiest way to see that is to split this up as 1/2 x plus 3/2. So we start at 3/2 and we go up 1 over 2. Now this is a little complicated because you're in the spaces between the lines. But if you know you're going to go up 1 and over 2, and you're starting in a half and you're ending up in another half of a number, if I just graph that little part, you see that we're going to end up on this point as well. So I've sort of manufactured another, they call it lattice points. Lattice points are the intersections of the grid itself. So now I can just use that point and do up 1 over 2. So up 1 over 2, that's the same one, that's nice. Up 1 over 2, up 1 over 2. Down 1 over 2, down 1 over 2. So I'm just using slope. That's all I'm doing. And there's the two graphs. Now there is a relationship between these two graphs. What you may notice is, for example, we have this point here, which is 0, -3, and we have this point over here, which is -3, 0. Perhaps there are some other points. Here is -7, -2. And here is -2, -7. What is the pattern? You are flipping around the x and the y. Well, that was actually enumerated. That's step 2. Interchange x and y. So when you find an inverse, exactly what you are doing is changing the x for the y, changing the y for the x, and you're just flipping them around. If you're thinking about this geometrically, then switching the x and the y corresponds to a reflection over the line y equals x. So here's the line y equals x, and we'll write this note. Inverses are reflections over the line y equals x. So any point that is on one function, you should be able to switch the x and y to find a point on the inverse function. And what you have to do here is take this line here and then flip it over that diagonal. Also notice that if the two functions, f and f inverse, intersect, they have to intersect on the line y equals x. That's because if they intersect, that means their y's are the same and the x's are the same, so they have to meet on the line y equals x. All right, let's look at example 8. Find the inverse of f of x is equal to the square root of x minus 3, then graph both f and f inverse on the same graph. So first we write this as y equals the square root of x minus 3. Interchange the x and the y. So we have x is equal to the square root of y minus 3. Next, we need to solve for y. Y is inside of a square root, so I'm going to square both sides. That gives me x squared is equal to y minus 3. Move the negative 3 from the right to the left. So we get x squared plus 3 is equal to y. So that's the inverse. F inverse of x is equal to x squared plus 3. Let's graph these on the graph. So first one is y equals the square root of x minus 3. That's the square root graph, shifted 3 units to the right, horizontal shift. Looks something like this. The inverse graph is x squared plus 3. So that would be vertical shift of plus 3. And the parabola. And, uh-oh, that ain't right, is it? Why is that wrong? Graphs of inverses have to be reflections over the line of y equals x. So and you start with the blue graph, because that's the one that was given. If you start with the blue graph, and you reflect it over y equals x, do you get the purple graph? No. So we have a problem. Where does the problem come from? I'll give you a hint. What's wrong with this function? What about it? Well, they're inverse. Well, they're partially inverses. They're partially inverses. What is it? Who said it? What did you say? Well, what property does the inverse function fail to have? It's not one-to-one. It is not one-to-one. A one-to-one function says that there can only be one x for each of the y's, right? Here we have 2 x's for each of the y's. And that's too many to compensate. Because remember, what we're dealing with is functions. When you switch around the x and the y, you still have to have a function. If you start with a function that is not one-to-one, and you did try to flip this around, let me use red on this one. If I did have this and I tried to flip it around, I would end up with this. That is not a function. That fails the vertical line test. So we don't have that. Get rid of that there. So the question is, what do we have to do to the result in order to make these inverses? And it's real simple. We just have to get rid of part of it. we have to get rid of one of these branches, either the left or the right. We have to keep the part that would be a reflection over the line y equals x, and that is this right half. If you see that we have a point here, oops, did not want to do that. We have a point here that is 4, 1. In the inverse graph, we need to have a point that is 1, 4. So we need to keep the right half of this graph. We take out the eraser, and we get rid of the left half. Now we are in business. Those are now inverse functions. We have to specify that algebraically, though. And the way we do that is the following. We say that f inverse of x is equal to x squared plus 3 on, and then we have to give a restricted domain. And that domain is the set of x's here. So the x's are going to start at x equals 0 and go off to the right. So that's 0 to infinity. They call this restricting the domain. We had to restrict the domain because the function we ended up with to be a candidate for our inverse function was not 1-to-1. If it's not 1-to-1, we can't flip it back. So we had to restrict the domain. This restriction of the domain provides the inverse for the square root of x minus 3. And obviously your restriction has to be one that is 1-to-1, but more importantly for this one, it had to be the exact restriction that provides the reflection. If it doesn't provide the reflection, then it's no good. All right, let's look at example 9. The function a of x is equal to x squared gives the area of a square where x is the length of the side. Find the inverse function a, find the value of a inverse of 25, and interpret. So let's rewrite this as y equals x squared. Switch the x's and the y's. Solve for y. So we get the square root of x is equal to y, and that is the inverse function for a. Question? No question? Okay. Now, do I need to use plus or minus? Think of the context of the problem. It's a square, an actual square. Nothing can be negative, so I don't use plus or minus. Everything is plus. The length of the sides of a square are plus, the area is plus, everything is positive. So we're good to go. And because we're only using plus, what does that mean? 1-to-1. Eh? Thank you. All right. Find a inverse of 25. So that would be the square root of 25. Square root of 25 is 5. Again, only using the positives. And the interpretation is the side of a square with area 25 is 5. So inverses switch around the context of the problem as well. The a function originally gave me the area given the side. A inverse gives me the side given the area itself. All right, example 10. The amount of water in gallons in a tank is given by the function w of x is equal to 1200 minus 30x, where x is the number of days since the tank was filled. Find the inverse of w, find the value of w inverse 900, and interpret. So we start with the function. It's going to be y is equal to 1200 minus 30x. Switch the x and the y. Solve for y. So I'm going to move the 1200 over. It moves over as a negative. divide both sides by negative 30. There are too many negatives on the left side. I'm going to take the negative from the bottom and I'm going to put it and multiply it through the numerator. When I do that, it's going to change the sign of everything on the top. The 1200 was negative, it's now positive. The x was plus x, that's now going to be minus x. And then rewrite that as an inverse. Finally, we need to compute the value of W inverse of 900 and interpret. So we'll plug this into the W inverse function. So 1200 minus 900 divided by 30. So 300 divided by 30 is 10. So the interpretation here is the number of days since the tank was filled when it has 900 gallons is 10 days.